Hey everyone, I've been working on a library called Polyform. I've recently added a marching cubes implementation to it. With this implementation, you can now build a lot more, say, organic looking models. It's not hard surface anymore. Um, I wanted to try and go through an example on how you might be able to use marching cubes, talk a little bit about marching cubes and its implementation, and how you might be able to create your own distance fields to influence the output of said algorithm. I'm probably going to put out these videos maybe once a month as I add new functionality to the library, or if I just get bored and want to quote unquote doodle around. I'm going to try making a virus looking model influenced by the COVID artistic rendering. But yeah, with that, let's get started. If we talk a little bit about marching cubes, and I am by far no expert, it is simply just a grid of values that are used to influence mesh generation. So we have a grid. This grid can contain any floating point value you want, positive or negative. Probably want to avoid nans and infinities, but other than that, whatever you want. You draw with marching cubes by setting values within this grid. So let's say I wanted to draw a sphere. One way you might think in a very crude low poly sphere is you'd mark all the values as 1, and then it would approximate around this grid around the 1 values, and you would have outputted a crude looking sphere. You can imagine if we upped the resolution of this grid and then increased the radius, we'd get a more accurate approximation of a sphere. We're going to take this a step further and instead do a gradient of values around what we would consider a sphere. So if we had a sphere with radius, let's say 1, instead of writing 1s everywhere, we'd say, here's my starting point, that's definitely 1, and then as we traverse away from the center point of the sphere, we write actually out the distance. So if we have a radius 1, then I don't know, this is 0.5 or something, and then over here would be 0.1, and then we might get into negative values. And then we use these values and we set a threshold in which we want the boundary to exist. So we might say a threshold of 0.2 would get us something like right here. And then we would then interpolate between these two cells to get the final vertex value. This will allow a much more smoother definition, but then we have a new variable to play around with, which is the threshold parameter, in which we set the boundary of these meshes. So there's a lot of different ways to play with this, and it might make a little more sense if it doesn't yet once we start writing code. So if we do that, I'm doing all this in the Polyform library itself in the examples folder. So code seen here, you can also see on GitHub and play around yourself. So I'll create a new folder called COVID. We'll create a new file. And this is package main, func main. And let's get started with the marching stuff. So in this library, it's called marching, and we're gonna create a new canvas. So we'll say marching, if I can spell, marching dot new marching canvas, and we have a resolution. So let's make that a variable. Resolution's an integer. It dictates how many cells that the marching cube canvas will have. You can think of this as the dimensions of an image. So it's integer. It's very absolute. There's no playing around with that. So we then also set a cubes per unit. So when we say something is of length 1, how many cubes does that actually influence? And so let's also break that out into another variable over here, because that'll influence our calculations. And we'll say 10 over here. So now we have ourselves, this could be floating point. So now we have ourselves a canvas, which is 100 by 100 by 100 cells. And when we say something is of length 1, we're saying actually occupy 10 different cells to accompany that unit of length 1. This will give us a more a higher resolution looking final mesh, with the caveat that we are going to be exponentially increasing the number of values we have to interpolate and calculate and triangulate and whatnot. So that's definitely a variable to play around with. If we say resolution's 100, then it's really 100 cubed cells that we're calculating, which I think is 1,000,000. I'm not actually sure. Wow, calculator takes longer to start than VS Code. Yeah, 1,000,000 cells. So if we are just to write ourselves a sphere on our marching cube canvas, this works in the concept of fields. So when we add a field, it's going for every single cell in the marching cube canvas, it's going to evaluate that field's value and add that value to the resulting canvas. So it's going to go down each single cell. If we go back to Paint, it's going to look at this cell. It's going to send it to the function we're going to pass it. It's going to get a value out and write it back. And it's going to do that for every single one until it's done. Which is why we also have a parallel function to also use for this if we get into a really intense calculation, which we'll start to build towards. But right now we can keep it non-parallel. A field is simply a function that, if we look at the function, takes a vector 3, returns a float. That's all it is. So you can define your own stuff. There's also helpers in the marching package, like sphere. So we're going to set its position, its radius, and what we call strength, and we'll play around with all those parameters. So first, getting position. The bottom left back corner of the canvas is at 0, 0, 0, and then the top right forward corner is at resolution, resolution, resolution. So if we wanted to get it in the center of the canvas, we actually have to do a tad bit of math between the resolution and cubes per unit. So we'll say center is resolution divided by cubes per unit. Can we do it the other way around? Can we make this a float? So that will translate it back to, say, how many units are in this canvas, which will be 10. So 100 divided by 10 is 10. So I'll do vector dot 1 multiply by a constant. And then we also would want to divide this by 2, which I know there's a prettier way of doing that. So that's our center. And then we're going to say the radius, let's just do 1, and let's say strength of 1, and we'll start to play around with this. So now we're just going to march it. We'll say canvas.march, and it's going to ask for that cutoff. That cutoff is what is the boundary in which I create a triangle. So we have values. So if I say the cutoff is 0.1, then as we cross the threshold in our cells from, say, 0.3 to 0.0, we will interpolate a boundary at 0.1. So this is going to return us a mesh. This is going to perform the whole march. And then we can write this mesh out to file. And let's say obj save. We'll do temp COVID. And we'll just call it covid.obj. And we'll do mesh. And we should have ourselves a mesh now. I'm going to start one of my utilities. It's just going to run stuff on save whenever I hit save on a Golang file. This is by Emerald Walk. It's a pretty helpful utility, and I've already configured this for this video. Let's see. Yeah, that's right. Cool. So now, if we say just save, it should run the command and then also open up the file, which it did over here. Let's see. There we go. Almost. There we go. Cool. So this is our file now. And so as we make changes to this, we'll see this update. So we have ourselves a sphere, and it's kind of, you can see the triangles, and that's because normals haven't been calculated. So let's just go ahead and take care of that. We'll say calculate smooth normals. And that's looking way better. So we have ourselves a sphere. Big whoop, that's kind of, you know, a primitive that exists anywhere in any kind of software you use around 3D. So let's take advantage of some of the features that marching cubes gives us. If we add another sphere, and we want to move it to the right by some amount, move vector 3. Let's move it to the I don't know, right one. Hit save. We notice that they're actually fused. There's not overlap, or how should I say this? There's no intersections taking place. They have written their values out to the marching cubes grid, and as we added both of these fields together, they overlapped, and then when the tessellation occurred over the boundaries. So let's say the intersection happened internally in the cell values themselves and not the mesh. And so because we're kind of just wrapping a mesh around these values, we don't have any mesh intersection. So you can get very smooth, blobby looking results from this. And now I have a great example on how to show you like what happens with these boundary conditions. So if I were to up the boundary condition, what should happen? Let's see. Yeah, so as we're upping the boundary condition, we're actually moving the cutoff inwards on the mesh themselves. And we can also do stuff like, you know, as we move the mesh to the right, we see it tear apart further. Well, that was too far, but you get the idea. Yeah, so we can now, you know, put a bunch of spheres down, and that's great and all, but let's now try creating the virus. So we have other primitives here such that we can draw to the canvas for. The other primitive is a line. So we're going to draw a lot of lines sticking out of the sphere. The lines themselves are going to be arranged in what is called like a Fibonacci spiral. It uses like the golden ratio and other types of math to place points evenly distributed on a sphere or a circle. And I might extend into 4 dimensions, I'm not actually sure. But it should give us an even distribution a, let's say, regular looking distribution that is pleasing to the eye. So instead of adding this sphere, let's go ahead and add a bunch of lines. So we're going to be using a number, I'm going to call these tendrils. I'm not sure of the actual proper name for what sticks out of the virus's body, but I'm going to call them tendrils, and I'll call it tendril count. And let's get some points and pass it the tendril count offset. So let's also create a new variable called virus width. Yeah, let's just do 2 for now. And that's it. All right. Points, I'll say tendril sites. I'm going to iterate over these tendril sites. And there should be a point, and we're going to use it to draw. Let's see. So we'll say canvas add field, and there should be a line, and our start will be the site. The end will be, let's see, there's also a direction associated with this, which should be the center. Let's see. Well, the center is 0, so actually it'll just be site dot normalize. Site dot, if I can spell, add direction, and then the radius, which will say like 0.5 and another strength of 1. Let's also bring that into another variable, tendril radius. Now, this is still going to be wrong because we actually have a center. So let's do the center of the canvas. So I'll take the site dot add. So we're combining the center. Okay, now let's break this into its own variable start. And we'll do start dot add direction. And let's actually, I want to create one last variable, which is tendril length. Let's do 1. So we're going to, it's normalized, so we just multiply by a constant, by the tendril length. And now I think this is all correct. I'm sure it's not once we hit save, but let's see. And it's taking a while now. Okay, actually that's correct. And it's looking kind of ugly, but that's fine. Okay, so we have actually gotten kind of almost there. We noticed that was kind of slow, and it's because we're going to be adding, let's see, 21 fields, extra fields to the marching cubes array, which can be slow because we're going to be iterating through that array 21 times. So instead, let's create ourselves a function in which we have this entire virus body a part of that function, and then we only have to write to the marching cubes once, and then we can write it in parallel. So we're going to come up with a single mathematical function which will define the shape of this virus. So let's create a new function that builds that function for us. Man, that's a mouthful to say. Let's see, virus field, and we'll move everything in there. Let's see. This is a sample.vec3 to float. That's what it's going to be. Sample.vec3 to float. And we can start by, let's see, we're gonna make an array of these and then sum them up all together. Because that's what's currently happening anyway. And then we're gonna go ahead and return this as well. I think it's none in here. Let's see, I think it's in the sample package. Sum vector float. There we go. I can never do it right. Is it this way? Yeah, okay. So let's pass in a virus width. Yeah, let's just make both of these parameters to our whole function. Okay, now we can create a field. All right, perfect. And we're going to pass it the virus width and the center. Yeah, of course I swapped those around. Okay, and let's move the tendril code into the virus field function, but instead of adding to the canvas, we're going to add to our array of fields. There we go. So now our virus field function writes everything all at once to the canvas, but you might be thinking, well, we kind of just changed the order of operations in which how we write, which is true, but now it's way easy to parallelize because we can split up the grid into a bunch of chunks that all get distributed across all threads available to the machine. So now when I hit save, yeah, runs faster. Okay, we have these tendrils popping out, but they don't look honestly all that great. It's all way too uniform. First, I'm going to fix some of the uniformity of the, let's say, virus itself by actually adding a bunch of smaller spheres to add, like, I don't know, acne looking bumps and make it look way more irregular. So let's create more Fibonacci points, and let's make it actually like half the tendril count. So if we have 20 tendrils, we'll have 10 of these irregularities messing with it. And I'll just call them irregular sites. I'm not sure. Let's iterate over those. And how should we do this? We're not going to be adding a line, we're going to be adding a sphere. And we don't really have an endpoint anymore. And do we do tendril radius? I don't know what that's even going to look like. Let's just see what this even looks like. Okay, yeah, that's definitely acne looking. I kind of want it less obvious on what's going on. First, I'm gonna multiply the tendril radius by 2, which will actually, that might do it. Let's see. No, that's worse. So we obviously don't want it occurring right on the surface. That's half the issue going on. So instead of adding, instead of using, yeah, the virus width, let's do the virus width times 0.75. And let's see. Okay, that helped out a ton. I think I'm going to actually do 0.5 and then also increase the radius by a smidge. Okay, I'm pretty happy with that. We don't have a uniform circle anymore. We have this blobby looking thing. but the tendrils are still pretty boring, so let's edit those. If you notice in some of these virus-looking things, at the tip of the tendrils, they have like, I don't know if they're grabbers or I don't know, teeth. I don't know actually how any of it works, but they stick out at the very end, and they're variable amounts. And so let's see if we can try to create those. So I think I'm going to break the tendril field itself into its own function. And what we have a start, a direction, and a radius. Yeah, okay. Start, direction, which are both vectors, and then a radius, and then I think that's a length on the end. And let's go ahead and yeah, okay. So we'll still have our line, and this is going to return us that, and also the fields. Yeah, so we'll start like this. I'm going to return just like how we did the other, the virus body. Okay, and then this should get us back to exactly where we were. It's just rearranged in a different way. No, okay, I did that wrong. Okay, let's see. We do start, add direction site. Oh man, what did I do wrong? It looks like it's all starting in the right place, but the it's probably going towards 0, 0, 0. Or actually, I actually don't know where it's going. Let's see. Okay, so I don't need to be doing start to add direction twice. I'm going to just pass direction here. And also, I'm going to keep direction normalized and choose yeah, how to use the length, because I'm not doing that here. So let's take the right there, and we're going to pass tendril length. Okay, and now we should be good. What is that last one? Strength. Okay, gotcha. So let's create a new variable called endpoint, which is the start dot add, and then we're going to do direction dot multiply by constant by the length. And this should get us back to where we were. Okay. So now let's try to add blobs at the end of each of these things. So we have the endpoint, we also have direction. If we want what we're going to try to achieve, let me create a new paint document. If we're going up like this, we're going to, this is kind of like a 3D view. We're going to try putting on a bunch of these blobby, plummy tendril things around a circle surrounding the tendril. So we're going to need the perpendicular vector from the direction coming out of the sphere, and then we're going to want to rotate around this direction at certain increments, creating spheres. So we're going to create a sphere here, here, here. To get started, let's just get the perpendicular axis. There's no way I spelled that right. Let's copy that spelling. And we're going to simply just, this should get us at least one. Endpoint, let's see, fields.append marching.sphere endpoint.add perpendicular radius of, let's just do the radius passed in, strength of 1, sure. And this should at least give us one of those blobby looking things at the end. Yeah, but they're way too offset. So let's change the distance. Let's see. Do we do it here? Where do I want to do it? I think I'll do it over here. Multiply by constant, and let's bring it in about half as far as it's coming out. Yeah. So now we have one of the multiple tendrils. I also don't like how big it is. So if we, let's say, its radius is going to be half of the tendril's radius. Yeah, that's too small. Okay. You know, we can play around with that for a while, but let's go ahead and add the others. So if we, let's see, let's create a new parameter called plumes or plums. I don't know what to call these. And we're going to say we need to go around in a circle, so the angle increment is going to be equal to math.pi times 2 all divided by the number of plumes. And we're also going to iterate over, let's see. All right. So we need to multiply, or we need to rotate this perpendicular axis now by the angle increment. So I think the new location will be, or what the rotation quaternion, let's see, new unit, let's see, there's a whole unit quaternion thing. If I can type today, let's see, unit quaternion from theta, there we go. Okay, so we pass it theta, which will be I multiplied by the angle increment, and the, oh, why the, I do not want the int version. Okay. Okay, and then it's going to want a vector, which will be the direction vector. So what we're going to do, let's see if we come back over to our drawing. We just said, you know, use this direction vector and rotate by a theta. And we're going to apply it to this thing. So it's going to rotate around the direction by a certain angle. That's what we're saying when we create this. So our new endpoint is going to be, let's see, let's call it plume site or something. Let's move all this math out of here and break it onto multiple lines. So we still want our endpoint. Let's add our endpoint in the end or something. So we're going to rotate our perpendicular, axis. Rotate perpendicular, and then we're going to multiply it, and let's normalize this because I'm paranoid. We're going to then move it in by 0.5 units, and then we're going to add in the endpoint. And I think that will do it. We just need to specify number of plumes, and let's do 3. Yeah. So this is a fun variable we can control. I'm going to tweak this a little bit to make it look a little more like how you see it in some of the images. And I realize this is like an artistic rendering of an artistic rendering. Like I know it's all kind of like everyone copying each other, and we get into the stereotype of what a virus looks like. I truly don't know what it should properly look like or what I'm doing. So first let's make the plumes a little bigger. So let's do 0.8 of the tendril radius. I might just go ahead and make it back to 1 and shrink the tendrils themselves. Actually, I kind of like that. Let's also, instead of putting it exactly at the endpoint, let's put it a little further forward. So if the tendril length is 1, instead of putting this at length of 1, we'll do like 1.1. So instead of endpoint, is there any way I can? I'm trying to think, can I just extend this endpoint vector? Am I thinking of that correctly? I don't think I can do that. Yeah. I'm like not the greatest at math. So we rotate, multiply by constant, then we're gonna add endpoint. And I guess, yeah, we can just multiply by constant, and then I say 1.1. No. Yeah, and everything's drifting off into that direction. So what do I need to do? This is what I have to modify before it gets added by the start vector. Okay, that's the whole issue. And so we'll do length times 1.1 over here, and that should fix it. Yeah. And now they're slightly going outwards, which I think I can now shrink them again. So let's do 7.5. Yeah, maybe, do I move them outward even further? Let's see, 1.2. And this is just stuff you can play around with, you know, and tweak however you want this to look. Okay, pretty aggressive looking. I feel like it's gonna grab me. This is kind of nightmarish. So I think that's pretty good. I'm going to now add some noise to just the tendrils themselves. Number of, let's add noise to the number of tendrils, size, and whatnot. So first, right now I've hard-coded it to be 3 over here, and let's just say the minimum will be 3 and the max will be 5. So I think I'll do number of plumes equal to 3 plus math.round 2 times ran.float. I'll be like, there we go. Yeah, and it thinks it's or it technically is a float because of this one. So let's cast that back to int. There has to be a nicer way to do this one. I'm not happy with that one. So we got 3s, we got 5s, do we have 4s in here? Yeah, we got 4s. Okay. That made it more nightmarish. I think I hate the 4 the most. Let's add variations to the size of each of these plumes. Let's see. So right now they're just radius times 0.5. Let's see, 0.75. Plume radius equal to radius times, and we'll do, let's say the minimum is 5, and they can grow as much as the radius, I think. I'll do that. math.rand, or that's a Unity library is talking me put random in the math, which always messes with me. Okay, times 0.5. So that will make it such that it will ever only be max radius of the tendril radius, I'm pretty sure. Let's see where that gets us. Yeah, okay, 0.5 is a little too low, but we're getting there. So I think I'll 7, and then let's just decrease it to 2. So we're in the range of 0.7 to 0.9 now. Yeah, I think that's pretty okay. Also, just due to the resolution of the marching cube cells, we're getting these kind of crappy blocking looking triangles coming out, so I think I'm going to just apply a smoothing step to this whole thing. So after we march, let's then do calculate, or is it just smooth? Smooth Laplacian, or however you pronounce it. And I'm just gonna guess on some numbers. We'll always calculate smooth normals in the end, just because that's after all the vertices are done being moved. Yeah, that looks way more smooth. And then also let's just play with the tendril length itself. And you know, we could, let's see. Yeah, let's just play with the tendril length itself. And also let's play with the tendril count itself too. Let's do int math.round 20 times rand float. So now we can say we have between 20 and 40 tendrils, and then the tendril length can be, let's change this down to 0.7. Let's do 0.8 plus, and let's do this whole thing again. Oh, I don't want to round though. 0.4, and then the radius, let's see. Yeah, let's just try it. Okay. So I think the tendril length always needs to be relatively long. Let's keep it at 1, minimum of 1. And then the radius, what do we have? 5? Let's make it 4 at least. And we're battling the resolution of the grid and all that. Let's see. Well, actually, that looks pretty high poly still. Yeah, I mean, we have 86,000 tries. What am I going wrong on? That's interesting. Is tendril length being used? Yeah. Am I passing it in wrong? Goes radius, then length. Yeah, radius and length. Interesting. Do not like what's going on. Is it strictly the radius messing up everything? Yeah, okay, the radius just really sucks. Okay. Alright, so we don't want the radius to go above probably 0.6. So we'll make it as low as 2. Okay. And we'll go back down to, oh, that is wrong. It's gonna write to it twice. Interesting. Okay, I'm just gonna hard code this to 0.5 for now. And 0.7. Alright, so we have this looking weird virus thing, but it's all one uniform color, so the last thing we're going to do is UV map this to a color gradient. To create our color gradient, I'm going to use the colors package / stack / whatever. We'll do this over here. We'll say colors. Or is it color stack? Or no, it's coloring, isn't it? Yeah. New color stack. And then coloring dot, yeah, new color stack entry. And I'll write out some stuff and explain it. And it'll be easy to explain once you're seeing it visually. So, RGBA. Let's just make it gray for now. Let's do 200, 200, 200, and then 255 for the alpha, and let's just do red over here. We'll just do bright red. Okay, let's debug this. Oh, yeah. Virus color. Debug, and the path is over here. So all debug does is we're going to write the image out to the file system, or the color gradient ramping to the file system to be easily seen. We're going to double the usage by also using it as the UV map. And so once we see the virus refresh, we know the image has been written, and we should also be checking each of these while if error not equal to nil. And I'll do it over here as well. I've just been assuming they work because I can visually check it. Oh yeah, okay. So if we go over to there we go. Okay, cool. So that's really weird. I don't know. Right as I close it. That's weird that it's struggling so much for an image. Okay. So if we look back at what we've done, we have created two color stack entries, both with weight of 1, both with fading of 1 on both directions. And this is order dependent, so we specified whitish gray first and then red. And so we have each of them equal to themselves. So how the math works out is there'll be a uniform blend between one and the other. I could say make the grayish portion take up 4 times as much as the red portion. And then if we hit save, and it does all its math, we should see the image to be updated. Right. Way more white than red. And I actually think I'm gonna keep it around there because I want that fade into the tendrils. So the UV mapping is gonna be pretty basic. I'm not gonna do anything intense. All we're gonna do is right at the center of the virus, it's gonna be white. And on the tendrils themselves, it's going to be red. So first we're going to what? We want to do this before the smooth Laplacian. We want to do it before the calculate normals. We're going to, we need to build our UVs themselves. And since we're basing the UVs based on the center, actually first we need to center this thing. So we're going to center the position attribute of the vertices. So what we've done, because this is off-center, because the bottom back left corner of the marching cubes grid is at 0, this is technically, if you remember, offset by this amount. So we're centering the geometry back, and now our math is going to be way easier. So let's go over all the positions themselves. Let's see. And so that's what we use scan for, and all scan is going to do is going to get called with each vertex position of the mesh, and we can actually build our UVs from that. And our UVs are going to be a vector 2. And we know our max tendril length is what? Oh man. 0.11 or 1.1 plus the virus radius is 2. It should be radius. Which means our max tendril length will be around like 1.3 or 3.3. Okay. I'm just gonna, this is gonna be pretty ugly. So, because everything's centered now, we know the vector, its distance from from 0, 0, 0 is how far we out are because we're in a circle. So if we do v dot length, and then we do divide it by 3.3, that should get us a value between 0 and 1. 1 should be on towards the right, the red portion of the image, and 0 should be towards the white part. So that's going to be our x variable because we're going from left to right, not up to down. So we're just going to say UVs append UVs. Oh, that's interesting. It's being weird. Oh, well, because I didn't make this array. That's why it's being weird. And we're going to create a new vector 2. Oh my gosh, come on. And our x is going to be that, and our y is just going to be dead center of the image. I don't think it really matters. I think you can make it any value you want. Now that we've calculated our UVs, we're going to set them. So set float2 attribute modeling dot text chord attribute UVS. All right, and then we're going to need to also make sure that it uses the map we've been generating. So let's do two things. Let's break this map name into a variable. Texture, let's just call it texture map. And then now we can use this in two places. Path.join. And we're going to now set the material over here. Set material. And we're going to call it COVID. And we're going to, let's see, color texture URI, texture map. And that might be everything, potentially. Let's see. And we're going to just get to play around with the values for the rest of it. Yeah. Okay. I mean, that was almost all the way. So here's the issue, or there's multiple issues. First, you notice the tips are white, and that's because we divided by 3.3, but apparently some of the plumes are extending past 3.3. So if I make this like 3.6, that might solve that. Let's see. Yeah, and honestly, that's probably good enough. The second issue I was going to highlight is that the body isn't purely white. So really what we should be doing is like, because the radius starts at like 2, we could do -2 over here, and then -2 over here, which brings up to 1.6, and that should make the body whiter. Let's see if that works in our favor. Almost. And now we're getting wrapping in the other direction. So if I make this, yeah, what do I want to make this? If I continue to subtract, I think the wrapping gets worse. So I need to decrease how much I'm subtracting. So I'll do 1.5, and we'll make this 2.1. And now it should be mostly wrapped around that gradient. Yeah, perfect. Okay, so that's a pretty simple UV map, and now we can play with colors. That's a pretty bright red. Let's see, and this is, I'm literally just about to show my workflow right here. We go to color picker, and I'm gonna go back to the bright red, but I'm gonna be way less reserved with it. Let's see, kind of like that, 230, 50, 50. Over here. And then I don't feel like that gray is gray enough, so I'm gonna, let's see, go over here. And then what else? I could add extra flare and color. I guess towards the tip, I could make it turn like purple. Let's see what that might do. We're gonna create a new stack entry. And then I'm gonna make this extremely tiny. So just as the tip is purple. And I'm going to do, yeah. Let's see what that looks like. Well, we don't get much of the purple. Oh yeah, we get tinges of purple on the edge. Yeah. So that's kind of it. That's all I wanted to go over today. If you watched to this point, I really appreciate it. I'm always kind of adding features to this library as I tackle different projects. So if you have a feature you want to see, or me tackle a specific thing to procedurally generate, I'm definitely interested in hearing it. And yeah, have a great day.